Hello, my name is Paul Geyer, and I'll be talking with you today about advanced wastewater treatment systems. This slide tells you a little bit about me and what I've been doing for the last few years. In wastewater treatment, it's generally characterized as consisting of four phases: preliminary treatment, primary treatment, and secondary treatment, and then tertiary or advanced treatment, which is what I will be talking about today. The tertiary treatment, most of it usually occurs after secondary treatment, but certain uh, procedures can be implemented in the primary or secondary treatment stages. For background information, just a quick picture of the overall wastewater treatment process. The basic treatment or primary treatment is a physical separation of undesirable materials from the wastewater stream using a grit chamber and sedimentation tanks after the wastewater stream is passed through coarser filtering media like trash racks. Secondary treatment typically consists of mixing of oxygen with the wastewater stream in order to reduce the large molecule contaminants to small molecule contaminants that can then be released into the environment without any adverse effects. One of the most common methods of secondary treatment is the activated sludge treatment. This figure shows the different tertiary treatment steps that can be employed, and most of them will be employed after the secondary treatment stage, but certain ones, basically those directed at phosphorus removal or nitrification, can be employed at the primary and secondary stages to supplement the basic primary and secondary treatments. This table indicates the various advanced wastewater treatment methodologies that may be employed. The abbreviations used across the top: SS is suspended solid, BOD biological oxygen demand, C chemical oxygen demand. Basically, these are measures of the biological contaminants in the wastewater stream. And then, of course, ammonia and nitrogen and nitrates and phosphorus, which are chemical contaminants, and TDS is total dissolved solids. The first method that might be employed is polishing ponds. Wastewater treatment ponds may be used as a practical and economical method for upgrading existing secondary treatment facilities to obtain improved organic and suspended solids removal. Both aerobic and aerobic anaerobic ponds can be used for this purpose. Aerobic, of course, indicating in the presence of oxygen, anaerobic indicating in the absence of oxygen. Ponds used for polishing purposes are subject to the same operating characteristics as those used for primary or secondary treatment, and the same precautionary design considerations must be applied. Here is an example of a polishing pond in a natural setting. This is an artificially constructed polishing pond. Post-aeration is a methodology that may be employed as one of the advanced wastewater treatments. This can be accomplished by either diffused, cascade, U-tube, or mechanical aeration. Diffused aeration is carried out in tanks 9 to 15 feet deep typically and 10 to 50 feet wide. The depth to width ratio is maintained typically at less than 2. with detention times in the post-aeration ponds of about 20 minutes. The maximum air requirement is approximately 0.15 cubic feet per gallon of wastewater treated. Mechanically aerated basins are typically 8 feet deep and require 15 to 50 square feet per aerator. Surface aeration is the most efficient mechanical aeration in terms of required horsepower, approximately 0.1 horsepower per 1,000 gallons of effluent. The drop required for cascade aeration in a stepped weir structure or in a rapidly sloping channel filled with large rocks or concrete blocks will depend on the desired oxygen uptake. 2 feet of drop will be provided for each milligram per liter of dissolved oxygen increase required. The next possible methodology that might be employed is microstraining. A microstrainer consists of a rotating drum supporting a very fine stainless steel or plastic screen. Wastewater is fed into the inside of the drum and filters radially outward through the screen with the mat of solids accumulating on the screen inside the drum. The solids are flushed into a removal trough at the top of the drum by a pressurized backwash system. From this trough, the solids are returned to the head of the system. Process effluent wastewater can be used for the backwash. Table 2, which you will see in a moment, provides performance data for several microscreen installations. This table indicates the performance parameters for microstrainers, the hydraulic loading for the different screening fabrics, 23 micron and 35 micron fabrics. The backwash water required, generally 3 to 6% of the average flow, and the backwash pressure is typically in the 15 to 50 psi range. The rotating drum speed 0.7 to 4.3 RPM being representative. Allowable head loss typically is 12 to 18 inches of water. The optimum hydraulic loss through the screen is 6 inches, and the optimum solids loading is 0.88 pounds per day per square foot at 6.6 gallons per minute per square foot. Microstrainers will be designed on the basis of not exceeding 10 gallons per minute per square foot of submerged screen area at design maximum flow. Multiple units will be provided and all units will be protected against freezing. Typical opening sizes for microstraining fabrics are 23, 35, and 60 microns. Respective number of openings per square inch being 165,000, 80,000, and 60,000. With the 23 micron screen fabric, the microstrainer can be credited for 75% solids removal. 60% removal is achievable using the 35 micron fabric, and maximum solids loading for microstraining of activated sludge effluent is 0.88 pounds per day per square foot at a hydraulic loading of 6.6 gallons per minute per square foot. An advantage of microstraining is the relatively low head loss, between 12 and 18 inches, with a 6-inch limit across a single screen. The efficiency of a microstrainer is determined by the hydraulic and solids loadings as well as by the filtering characteristics of the influent. Microstrainers will not remove colloidal material or small micron-size algae. Microstrainers are also adversely affected by fluctuations in influent composition and quality. Hydraulic control of microscreening units is effected by varying the drum speed in proportion to the differential head across the screen. The controller is commonly set to give a peripheral drum speed of 15 feet per minute at 3 inches differential and 125 to 150 feet per minute at 6 inches. In addition, backwash flow rate and pressure may be increased when the differential reaches a given level. The operating drum submerge is related to the effluent water level and head loss through the fabric. The minimum drum submergence value for a given installation is the level of liquid inside the drum when there is no flow over the effluent weir. The maximum drum submergence is fixed by a bypass weir which permits flows in excess of unit capacity to be bypassed. At maximum submergence, the maximum drum differential should never exceed 15 inches. Effluent and bypass weirs should be designed as follows. Select drum submergence level, 70 to 75% of drum diameter for no flow over the effluent weir. Locate the top of the effluent weir at the selected submergence level. Determine the maximum flow rate. Size the effluent weir to limit liquid depth in effluent chamber above the weir to 3 inches at the maximum flow rate. Position the bypass weir 9 to 11 inches above the effluent weir, 3-inch head on effluent weir maximum flow plus 6 to 8 inch differential on drum at maximum drum speed and maximum flow. Size the bypass weir length to prevent the level above the effluent wire flow exceeding 12 to 18 inches at peak maximum flow or overflowing the top of the backwash collection hopper. For backwashing, backwash jets are directed against the outside of the microscreen drum as it passes the highest point in its rotation. About half the flow penetrates the fabric, dislodging the mat of solids formed on the inside. A hopper inside the drum receives the flushed off solids. The hopper is positioned to compensate for the trajectory that the solids follow at normal drum peripheral velocities. Microscreen effluent is usually used for backwashing. Straining is required to avoid clogging of backwash nozzles. The inline strainers used for this purpose will require periodic cleaning, and the frequency of cleaning will be determined by the quality of the backwash water. The backwash system used by Zurn, a major supplier in this area, employs 2 header pipes. One operates continuously at 20 pounds per square inch, while the other operates at 40 to 55 pounds per square inch. Under normal operating conditions, these jets operate at 35 pounds per square inch. Once a day, they are operated at 50 pounds per square inch for a half an hour to keep the jets free of slime buildup. Should this procedure fail to keep the jets clean, the pressure is raised to 55 pounds per square inch. At this pressure, the spring-loaded jet mouth widens to allow for more effective cleaning. Backwash pressure can be increased to compensate for heavy solids loadings which require higher pressure for thorough cleaning. The superiority of the higher pressure system is manifested by the following. Operation at 50 pounds per square inch as opposed to 15 pounds per square inch increases the process flow capacity 30%. Suspended solids concentration in the backwash can increase from 260 milligrams per liter at 15 pounds per square inch to 425 milligrams per liter at 50 pounds per square inch. Water consumption of the jets as a percent of process effluent decreases from 5% at 15 pounds per square inch to 2% at 50 pounds per square inch. In general, backwash systems are operated at as low a pressure as possible, consistent with successful cleaning. High pressure operation incurs added system maintenance, particularly jet replacement, and is used only as needed. Over a period of time, supplemental cleaning consisting of cleaning of the screen fabrics may become clogged with algae and slime growths, oil and grease. To prevent clogging, cleaning methods in addition to backwashing are necessary. Ultraviolet lights may be employed in tandem with micro straining. They reduce clogging from algal and slime growth. The use of ultraviolet light lamps placed in close proximity to the screening fabric and monthly removal of units from service to permit screen cleaning with a mild chlorine solution is recommended. While most literature sources say ultraviolet lamps are of value, One authority feels these lamps are uneconomical because they require frequent replacement. Where oil and grease are present, hot water and/or steam treatment can be used to remove these materials from the microscreens. Plastic screens with grease problems are cleaned monthly with hot water at 120 degrees Fahrenheit to prevent damage to the screen material. Downtime for cleaning may be up to 8 hours. Filtration is the next advanced wastewater treatment methodology that we will discuss. The basic design parameters to consider are the following: type and size of filter media, depth of filter, rate, duration, and timing of backwash, filter run duration, filtration rate, and type of chemical pretreatment dosage required. With coarse media filtration, certain general design considerations apply. Filter media size will influence filter performance. Smaller media will achieve better suspended solids removal but will involve increased pressure drop and head loss buildup. Therefore, a balance between removal efficiency and hydraulic loading rate must be attained. For sewage applications, coarser media, higher flow rates, and longer filter runs will be used. Chemical treatment of the feed water may be necessary to improve effluent quality. Coarse media particles must have an effective size of approximately 1.3 millimeters with a uniformity coefficient of approximately 1. Sand or anthracite coal may be used, with coal giving a poorer solids removal but producing less pressure drop. Refer to the EPA Process Design Manual for Suspended Solids Removal for additional information regarding media specifications. The design application rate for coarse media filters will be typically 5 gallons per minute per square foot at design maximum flow. Single media coarse sand filters will be generally credited with 60% removal of suspended solids when the sand media size is no greater than 1 millimeter and the flow rate is no greater than 4 gallons per minute per square foot. Biochemical oxygen demand removal efficiencies will be dependent on the biochemical oxygen demand fraction of the suspended solids that is removed, since dissolved organic materials generally pass through the filter. With respect to multimedia filtration as compared to single media filtration, it will provide better suspended solids removal with longer filter runs at higher flow rates. A 75% suspended solids removal efficiency with multimedia filtration will be an acceptable design allowance for a design application rate of 5 gallons per minute per square foot. Filter aids such as alum can be used to increase removal efficiency. An application rate of 6 gallons per minute per square foot at maximum design flow will be utilized typically for design. Typical design parameters for multimedia filtration processes are given in tables 3 and 4, which you will see in a moment. Table 3 indicates typical multimedia designs employing coal, sand, and garnet of the different sizes and meshes indicated. Table 4 provides performance parameters for multimedia filtration. Hydraulic loading, typically 4 gallons per minute per square foot. Pre-treatment required is removal of settleable solids. The depth of filter media 30 to 36 inches, length of run 10 to 15 hours, terminal head loss 6 to 8 feet of water, and the backwash rate 15 GPM per square foot. Upflow filtration utilizes a pressurized wastewater feed with flows in the upward direction. Upward flow overcomes the fine to coarse particle size distribution disadvantage of single media filters. The media used is sand on top of gravel, with some models containing a grate on top of the sand layer to keep it compacted during filtration. This type of filter will achieve an average suspended solids removal of 85% and is capable of higher solids loading than conventional filters. The maximum design filtration rate is going to be typically about 8 gallons per minute per square foot. Continuous upflow air wash filters are also available in this category. All filters, with the exception of the upflow type, will require a reverse flow or backwash rate of 15 gallons per minute per square foot. An increased application or forward wash rate of 25 gallons per minute per square foot will be used for upflow filters. The required design duration of the wash cycle will be 8 minutes. The source of wash water in sewage filtration applications will be filter effluent or chemically coagulated and settled effluent rather than secondary effluent, to ensure that the filter wash supply will always be free of large quantities of suspended solids. A filter wash flow indicator should be included so that the operator can be sure that the desired wash rate is being maintained at all times. The wasted wash water must be reprocessed. Storage facilities will be required with filter wash wastewater returning to process at a controlled rate not to exceed 15% of the inflow. Provisions must be made to store the incoming flow during the filter wash cycle, or if there are no parallel units, to increase the rate on the other filters during the washing cycle. Either mechanical surface wash equipment or air scouring facilities will be provided as part of the backwashing design considerations. The next methodology of advanced wastewater treatment is activated carbon adsorption. Use of activated carbon adsorption will be based on carbon column studies performed on the waste with the type of carbon that is to be used in the operating process at the site proposed. With the downflow configuration, carbon adsorption beds will accomplish filtration as well as adsorption. This generally is an inefficient use of the activated carbon and will require frequent backwashing. When the feedwater suspended solids concentration is greater than 50 to 65 milligrams per liter, solids removal pre-treatment must be provided. Downflow carbon adsorption processes operate at hydraulic loadings of 2 to 10 gallons per minute per square foot of column cross-section area. The columns must be maintained in an aerobic condition to prevent sulfide formation. This will be accomplished by maintaining dissolved oxygen levels in feed and backwashing waters. Upflow carbon adsorption can be operated in 3 different modes. At hydraulic loadings less than 2 gallons per minute per square foot, the carbon bed remains packed at the bottom of the column, providing filtration as well as adsorption. This filtration can cause backwashing problems. At hydraulic loadings of 4 to 7 gallons per minute per square foot, the carbon is partially expanded and suspended solids pass through the bed. At loadings greater than 7 gallons per minute per square foot, the carbon bed is lifted. Upflow carbon beds are usually operated in the expanded bed or partially expanded bed mode and normally require no backwashing. However, periodic backwashing is helpful in removing carbon fines. Post-filtration will be provided to remove suspended solids from the effluent. A pulsed bed is defined as an upflow carbon adsorption system where a layer of exhausted carbon is withdrawn from the bottom of the carbon bed, with a regenerated layer being added to the top of the bed. This technique approximates countercurrent operation and is a nearly continuous process. Gravity flow systems have the advantage of eliminating the need for pumps and pressure vessels. The restricting factor in gravity flow is head loss. For this reason, pretreatment for suspended solids removal is required. Gravity flow systems can either downflow or upflow. The upflow expanded bed configuration will facilitate maintenance of a constant head loss. Pressurized flow systems will offer more flexibility in process design by operating at higher flow rates and over wider ranges of pressure drop. Series and parallel arrangement of activated carbon adsorption units are feasible. Carbon contacting beds can be arranged as single stages independently operated or as multi-stages either in series or in parallel. Series configurations achieve more complete organic removal and will be used when carbon adsorption is required to remove 90% of the total plant organics. Economic studies indicate that two-stage series operation is the least expensive in terms of operating costs. For lower levels of treatment, single-stage parallel contactors staggered in their status of operation or degree of exhaustion can produce the desired product by blending of individual effluents. Activated carbon is regenerated in a step heating process. Refer to the EPA Process Design Manual for carbon adsorption for design details. Carbon regeneration systems include preliminary dewatering of the carbon slurry to a moisture content of 40 to 50%, heating in a multiple hearth furnace to 15 to 1700 degrees Fahrenheit, quenching of regenerated carbon, and recycle to contactors. The regeneration process requires 3,200 British thermal units, BTUs, for burning off the impurities and 1 pound of steam per pound of regenerated carbon. Air pollution control equipment is required, usually an afterburner and a wet scrubber or bag filter. The carbon is usually transported within the system as a slurry at velocities between 2.5 and 10 feet per second. Lower velocities make the system vulnerable to solids deposition, and higher velocities cause abrasion in pipes. Velocities of 3 to 4 feet per second with 4 pounds of water per pound of carbon, 0.5 gallons of water per pound of carbon, are recommended. The carbon slurry can be stored before and after regeneration, or it can be transported directly to and from the contactors. The latter arrangement requires at least 2 separate contactors and is a significant cost factor in pressurized systems. Backwashing frequency is determined by head loss buildup, with lower flow rates usually allowing less frequent backwash. Backwashing is supplemented by surface washing and air scouring, and the complete operation lasts 15 to 45 minutes. Backwashing should provide 30 to 50% bed expansion while consuming no more than 5% of normal feed rate, for example 15 to 20 gallons per minute per square foot. Effluent can be used for backwash and then returned to the primary treatment stage. Where practical, a carbon column study should be conducted on the waste to be treated to determine the process design parameters. These studies should use the type of activated carbon that will be used in operating the full-scale plant. Pretreatment will be provided as necessary to keep the suspended solids concentrations below 50 milligrams per liter, unless the carbon bed is to be used as a filter also. The carbon will be 8 by 30 mesh granular carbon, unless carbon column studies show a different size to be more effective. Contact time is the most important design factor affecting organics removal and should be determined empirically for the particular situation. Typical values range from 18 to 36 minutes. Hydraulic loadings between 2 and 10 gallons per minute per square foot are acceptable. There appears to be little effect on organics removal in this range. The main consideration is with head loss buildup. Gravity flow systems are limited to hydraulic loadings less than 4 gallons per minute per square foot. Carbon requirements range from 250 to 350 pounds of carbon per million gallons treated. 300 pounds per million gallons is the preferred value. The adsorption capacity of carbon is affected by several factors and should be determined experimentally for each particular wastewater to be treated. Factors which influence adsorption include surface area, nature of the material to be adsorbed, the adsorbate, pH, temperature, the nature of the carbon, the adsorbent, and complexity of material to be adsorbed. The adsorption capacity of carbon per cycle usually ranges from 0.25 to 0.87 pounds of chemical oxygen demand contaminants removed per pound of carbon applied. To obtain guidance regarding the selection of the type of activated carbon to be used in bench scale or pilot scale studies, refer to Chapter 4 of the EPA Process Design Manual for Carbon Adsorption. The effluent quality requirement will determine the required contact time, and this in turn will set the approximate total carbon volume. The hydraulic loading will determine the total cross-sectional area and total carbon bed depth. The total bed depth can be divided between beds in series, and the total cross-sectional area can be divided into separate carbon beds in parallel. Vessel heights should provide for bed expansion of 50%. Contact tanks should have length to diameter ratio of between 0.75 and 2.0, with carbon depth usually greater than 10 feet. The tanks should be constructed of concrete or lined carbon steel. Typical coating materials range from a painted coal tar epoxy to laminated rubber linings. The carbon transport system must be designed to resist the abrasiveness of carbon slurry. More specific design details can be obtained from the EPA Process Design Manual for Carbon Adsorption and from equipment manufacturers. The next advanced wastewater treatment methodology we will discuss is phosphorus removal. As to general approaches, mineral addition and lime addition are the principal methods for in-plant removal of phosphorus from wastewater. The most commonly used of these metal salts are alum, a hydrated aluminum sulfate, sodium alumate, ferric sulfate, ferrous sulfate, ferric chloride, and ferrous chloride. Mineral addition is usually followed by anionic polymer addition, which aids flocculation. The pH may require adjustment depending on the particular process. In lime addition, phosphorus removal is obtained through the chemical precipitation of hydroxyapatite. When designing the phosphorus removal system, consideration must be given to the phosphorus levels in the system effluent suspended solids. Additional information may be found in the EPA Process Design Manual for phosphorus removal. With regard to mineral addition using aluminum, the theoretical requirement for aluminum in the precipitation process is a mole ratio of aluminum to phosphorus of 1:1. Actual case histories have indicated considerably higher, up to 2:1, than stoichiometric quantities of aluminum are needed to meet phosphorus removal objectives. Alum is the aluminum additive most frequently used, with sodium aluminate being substituted when alum addition would force the pH too low for other treatment processes. The theoretical weight ratio of alum to aluminum is 11:1, and in practice alum weight ratios in the range of 13:1 to 22:1 depending on the degree of removal desired, have been needed. For higher removal efficiencies, the aluminum to phosphorus ratio must be increased. Table 5 lists the aluminum to phosphorus and iron to phosphorus ratios required for 75, 85, and 95% phosphorus removal. Laboratory, pilot plant, or full-scale trial runs are often necessary to determine the most effective mineral dosages. Table 5 indicates the mineral to phosphorus ratios for given removal efficiencies for aluminum to phosphorus and iron to phosphorus. In the primary treatment stage, the mineral is added directly to the raw sewage, which is then mixed, adjusted for pH if necessary, flocculated, and clarified. The mixing and flocculation are to be carried out in specially designed units or within existing systems at appropriate locations such as manholes, partial flumes, or pre-aeration tanks. For maximum phosphorus removal, the mineral addition will be downstream of return streams such as digester supernatant. The required procedure for mineral addition at the primary stage is as follows. Add mineral to raw sewage and mix thoroughly. Add alkali if necessary for pH adjustment 10 seconds later. Allow reaction for at least 10 minutes. Add anionic polymer and flash mix for 20 to 60 seconds. Provide mechanical or air flocculation for 1 to 5 minutes and deliver flocculated wastewater to sedimentation units. The advantage of removing phosphorus at the primary stage are the flexibility of chemical feeding, the adequate detention times and mixing conditions available, the reduced suspended solids and biochemical oxygen demand loading on the ensuing secondary treatment stage, and the ease of process instrumentation. The principal disadvantage is that a significant portion of the phosphates is not in the orthophosphate form at the primary treatment stage and therefore does not precipitate easily. Mineral addition also causes increased solids production, 1.5 to 2.0 times the weight of normal primary solids, and the solids density increases with increasing aluminum dosages. Solids increases attributable to aluminum addition are about 4 pounds per pound of aluminum added, up to stoichiometric proportions, after which the weight gain is less. The addition of alum to the primary stage generates large quantities of metal hydroxide sludge, which is difficult to dewater. The advantage of mineral addition to the activated sludge process are enhanced sludge removal properties, shorter residence times, more effective phosphorus removal because of sludge recycle, relatively small additional solids production, which improves solid density and dewaterability, and flexibility to change conditions. The extra solids production, however, does involve additional sludge handling, just as when alum is added at the primary stage. In the activated sludge process, the chemical is added near the discharge points into the aeration basins. Mixing of the chemical and wastewater must occur in the basin, but premature precipitation must be prevented. Phosphorus capture will occur primarily in the sedimentation units following aeration in the basin. For trickling filter plants, it has been demonstrated that precipitation in the final clarifier can be both effective and controllable as per EPA Manual 670/273-060. Orthophosphate predominates at this point and it precipitates readily. Also, biodegradable detergents, which can interfere with precipitation, are largely absent. If underflow solids from a dosed final clarifier are returning to the primary clarifier, it will result in unusually effective clarification there. If the operation is not done effectively, poorly treated effluent can escape into the receiving water. in order to allow for incorporating the advantages of chemical treatment in both the primary and secondary clarifiers. Provisions for future installation of chemical addition and mixing facilities will be provided at the primary clarifier. Facilities or provisions for mineral addition to both primary and secondary clarifiers will provide flexibility of operation. Chemical treatment in both clarifiers can then be used if experience shows it to be the most effective technique at the particular plant involved. Initially, equipment will be provided only at the secondary clarifier unless bench studies or pilot plant operations show a more effective performance at another location or show the necessity of chemical feed at the primary clarifier also. With addition at the final settling basin, phosphorus removal is very effective because most of the soluble phosphates are in the orthophosphate form, which is the easiest to precipitate. The general procedure for mineral addition is essentially the same as in the primary stage. A surface overflow rate of 500 gallons per day per square foot should be used to size the final settling basin. With regard to mineral addition using iron, the iron requirements, the theoretical requirement for iron and phosphorus precipitation in terms of mole ratio of iron to phosphorus is 1:1 for the ferric ion and 3:2 for the ferrous ion. Actual plant results indicate that the mole ratio for the ferrous ion is closer to 1:1. With the same mole ratio for ferrous and ferric ions, the weight ratio of iron to phosphorus is 1.8:1. As with aluminum, however, experience has indicated that the weight ratios are higher. The optimum pH range for ferric iron precipitation of phosphorus is 4.5 to 5, and for ferrous iron about 8.0. Ferrous salts cause a lowering of pH and may necessitate addition of alkali. However, alkali addition is not necessary when there is a subsequent aeration step. Addition of ferric forms of iron tends to yield a fine light flock which does not settle well, but subsequent addition of lime and/or a polymer aids flocculation and settling. Ferrous iron addition may present residual problems in that excess ferrous ions may not hydrolyze and settle out at a pH lower than 8.0. Lime addition will raise the pH and alleviate this problem. Ferrous salts yield good results when oxygen is available, such as in the activated sludge process. Ferric and ferrous iron addition together with lime or polymer flocculation aids is particularly applicable to primary treatment without a subsequent activated sludge step because there is little effluent flock carryover. However, for certain installations it is preferred that chemical addition follow the biological reactor. With regard to the cost and availability and mineral selection and dosages, the choice of minerals should be based on the cost of the materials, availability of the materials, and the process performance. Cost and availability will be determined for each particular situation. Aluminum and iron salts are in the same cost range, with aluminum salts somewhat more expensive. Both aluminum and iron additives will produce soluble side products in the form of chlorides, sulfates, and sodium compounds, as well as some free acids and alkalis due to hydrolysis. These side products are seldom a serious problem, however, and can be controlled by adding only the proper amount of chemical and through the use of the automatic monitoring instrumentation. Alum and iron chloride are the most commonly used mineral salts, and both cause an alkalinity drop, which can lower pH if the buffering capacity is not adequate. Iron tends to yield higher effluent residuals, around 6 milligrams per liter as iron, than aluminum, less than 0.5 milligrams per liter as aluminum. Aluminum addition produces 30 to 50% less additional solids than iron additives, and the sludge has greater dewaterability and sludge density. Aluminate and alum produce about the same amount of sludge, but the aluminate sludge is considerably less dense. Alum addition tends to produce better effluent clarity than does aluminate. Mineral dosages will be determined by the weight ratios and, when applicable, by pilot plant and laboratory studies and full-scale plant test runs. Alum dosages are usually in the range of 150 to 250 milligrams per liter for an average influent phosphorus concentration of about 10 milligrams per liter. Typical iron dosages range from 10 to 25 milligrams per liter as iron. These typical dosages will accomplish 80 to 90% phosphorus removal. Greater phosphorus removal down to residuals less than 0.5 milligrams per liter can be obtained by using multimedia filtration techniques. Refer to the EPA Process Design Manual for phosphorus removal. With regard to lime treatment as an approach to phosphorus removal, lime addition accomplishes phosphorus removal through the chemical precipitation of hydroxyapatite. Although the solubility product theoretically determines the amount left in solution, the actual determining factor in removal efficiency is the efficiency of the clarifiers. The precipitation of phosphorus by lime requires a high alkalinity, with a pH of 11 being optimum. Therefore, the lime dosage is not a function of phosphate concentration, but rather it depends on the amount of lime necessary to attain the proper pH. This in turn is largely dependent on influent wastewater alkalinity. Typically, a lime dosage of as much as 400 milligrams per liter as calcium oxide will be necessary to attain a pH of 11. Phosphorus removal by lime addition has these advantages: no soluble side products, improved oil, grease, and scum removal, less corrosion in sludge handling systems, and recovery of the lime. The disadvantage is that the high pH required for lime addition has a detrimental effect on any downstream biological treatment process, including activated sludge, trickling filters, and sludge digestion. Lime treatment can be either a single stage or a two-stage process, depending on the degree of phosphorus removal required and the alkalinity of the wastewater. A low alkalinity of about 150 milligrams per liter as calcium carbonate will yield a poorly settleable flock. A high alkalinity requires subsequent recarbonation, CO2 contact, to lower the pH, which in turn causes calcium carbonate to precipitate and requires a second stage to settle out the calcium carbonate sludge and provide better clarification. A high alkalinity, 200 milligrams per liter as calcium carbonate, on the other hand, will yield a good settling flock at a pH as low as 9.5, thus eliminating the need for a second stage since the calcium carbonate precipitate will come out in the first stage. This process will be considered as an alternative where the use of mineral salts would not be satisfactory. Figure 2 indicates the feed water alkalinity versus lime dose relationships. The general procedure for single-stage lime treatment for phosphorus removal purposes is as follows. Add lime slurry to the wastewater as needed to obtain a pH of 9.5 to 10.5 and provide rapid mixing for about 30 seconds. Provide flocculation and sedimentation. If recalcination is used, thicken the sludge to 8 to 20% solids, centrifuge to 30 to 40% solids, and then recalcine to calcium oxide and calcium hydroxide. This is usually not economical for smaller installations. After sedimentation, recarbonate for about 15 minutes to obtain the pH necessary for subsequent treatment or discharge. With regard to two-stage lime treatment for phosphorus removal purposes, the procedure is as follows. Add lime to the wastewater as needed to obtain pH equal to 11 to 11.5 and provide mixing for about 30 seconds. Provide flocculation and settling. Sludge can be recalcined as in single stage. Provide recarbonation for 5 to 15 minutes to obtain a pH of 9.5 to 10. Provide a second stage settling with sludge recalcined as required. And again recarbonate for about 15 minutes to obtain the pH required for following treatment and ordinary discharge. Lime addition at the primary treatment stage is effective in removing from 80 to 90% of phosphorus. It also reduces biochemical oxygen demand by 50 to 70%, suspended solids by 85%, nitrogen by about 25%, and coliforms by as much as 99.9%. However, the high pH necessary for this type of treatment causes difficulties in downstream biological treatment processes. Neutralization, that is recarbonation, may be required before biological treatment. Primary lime treatment will reduce the organic load on the secondary treatment stage and will reduce secondary sludge by almost half. The primary sludge, however, will increase about threefold. With lime treatment in the primary treatment stage, recalcination is often impractical because calcium carbonate may not precipitate in sufficient quantities. A more effective and flexible technique is lime addition as a separate stage after secondary treatment. The advantages of this are the flexibility of operation and the backup function of the secondary system. Either single-stage or two-stage lime treatment can be used. However, two-stage treatment is preferred because it produces a better clarified effluent, has more lime recovery potential, and provides higher phosphorus removal efficiencies. The mixing, flocculation, and settling units can be separate or integrated units. The integrated type unit, an upflow clarifier, works well, but sludge blanket problems are encountered. Integrated units that work without sludge blankets and separate units are recommended. Lime addition in the primary treatment can make use of existing process units or separate units can be used. Modifications such as sludge recycle to the flocculation chamber and polymer addition improve settleability of the sludge and thereby improve phosphorus removal efficiency. Mineral addition can also be used after primary treatment with lime to improve overall phosphorus removal efficiency. For additional information, refer to the EPA Process Design Manual for phosphorus removal. The lime requirement can vary over a wide range depending on operating pH and water composition. Alkalinity affects the lime dose, as can calcium hardness. 1 part by weight of calcium carbonate can react with from 0.89 to 1.79 parts of bicarbonate alkalinity expressed as calcium carbonate. The lower value applying to very soft waters and the higher value to very hard waters. In addition to the reaction of lime with hardness, other competing reactions occur in lime treatment of wastewater. Also, there may be incomplete reaction of the lime. These complications make calculation of lime dose difficult. Consequently, determination of lime dose is largely empirical. Some approximate values are given in the U.S. EPA Process Design Manual for phosphorus removal. The lime dose will usually be in the range of 300 to 400 milligrams per liter as calcium oxide for two-stage treatment, and from 150 to 200 milligrams per liter where single-stage treatment is satisfactory. Recarbonation is discussed in detail in the EPA Process Design Manual for phosphorus removal. The next advanced wastewater treatment methodology that we will look at is land application systems. The use of land and biomass growth upon and within the soil has a long and interesting history. This history, as well as much more detailed treatment of land application of wastewaters, is covered in the appropriate EPA publications. It should be noted that this discussion is intended to be supplemented by the U.S. EPA Manual for Detailed Design Criteria. This has been done because of the broad site-specific design considerations that exist for land application systems. There are health hazards and regulatory limitations that are encountered with land application systems. Because land treatment of wastewater entails a higher risk than other treatment processes of introducing pathogenic microorganism and toxic chemicals into groundwater and surface water, land treatment system design must carefully consider all possible means to prevent water supply contamination. Additionally, state and local health regulations often dictate land treatment process design criteria. Therefore, these regulations must be consulted early in the design phase and frequently throughout construction and operation to ensure consistent compliance. Land treatment of domestic wastewater which has undergone secondary treatment and sludges from wastewater treatment plants may involve one of the following modes. Land treatment of wastewater after primary treatment is acceptable for isolated locations with restricted access when limited to crops which are not for direct human consumption. First, slow rate filtration, rapid infiltration, overland flow, use of wetlands, and subsurface incorporation. Two methods of land treatment apply to sludges: composting and land spreading, and subsurface incorporation. Slow rate processes essentially mean irrigation of crops, grassland, or forest land based upon the demand of the vegetation. Typical application methods involve pipeline to row crops, surface distribution along furrows and ridges on the contour, sprinkler irrigation, or drip irrigation. Sprinklers and drip irrigation require that wastewater is quite free of solid suspended matter. In arid to semi-arid areas, utilization of such wastewaters, even if only to recreational areas, should be seriously considered both for conservation and to improve local aesthetics. Rapid infiltration, often called infiltration percolation, involves almost complete saturation of the soil column and potentially also the rock beneath. A thick, sandy regolith with low water table is required. Freshwater wells, well points, and springs must be sufficiently far away so as to not receive contamination. Often the object is to renovate water and to recapture the effluent again with special wells or under drains for reuse in cooling or irrigation. Rapid infiltration may often be used to prevent the intrusion of saline water on an atoll or sandy coastal plain site. Although vegetation utilization is not planned for rapid infiltration systems, studies have shown that use of deep-rooted plants, an active root and humus mat, and tolerant vegetation will much improve the quality of the recovered water. Vegetation must be carefully selected, and of course some water will be lost to evapotranspiration and to production of biomass, but the living filter will produce excellent quality water below the surface. With regard to overland flow, this process involves a surface phenomena and depends strongly on vegetation and the myriad organisms in the humus layer of a sloped field. Wastewater is applied over the upper reaches of sloped terraces carefully constructed to match the contour of the land. Runoff after surface flow is collected in ditches. Application may be from linear pipeline sprayers, plastic trickle irrigators, or using rotating sprinklers. Overland flow could be used in forested land or to produce forage. Like the biofilter concept, such systems not only reduce suspended solids, kill pathogens, and lower biochemical oxygen demand, but dramatically lower levels of nitrogen and phosphorus. With regard to natural wetlands, although true wetlands occupy only 3% of U.S. land surface, these areas offer great potential for recharging water tables and refurbishing wastewaters. Purposeful utilization of the ecologically complex habitats is new to modern man, who began to recognize around 1970 that fresh and saltwater marshes, swamps, peat bogs, cypress domes, and strands could provide excellent and very inexpensive treatment. With proper system management and design, wetlands can treat wastewater without damaging the existing ecology. In fact, nutrient addition can enhance productivity and increase wildlife and overall aesthetic value. During cold periods, wetlands cannot handle discharges, therefore storage in lagoons is necessary. Loading capacity has been estimated at about 40 persons per acre. Artificial wetlands have been constructed on sandy soil using impervious plastic liner. Others have been made of less pervious silt and lined with clay. Peat bogs have been very successfully used in Minnesota and in Europe. In deep swamps, natural or artificial, water hyacinth, duckweed, Wolfia, and other aquatic plants have been used to remove nutrients from wastewater. Limitations of such vegetational techniques have been placed at about 35 degrees north latitude. Basically, the subsurface systems involve either soil mounds or subsurface filters, and such systems are used where adverse soil conditions exist, such as high water table, relatively impermeable clay-rich soils, or shallow bedrock. With regard to composting of sludge, where sufficient inexpensive biomass is available, such as bark, wood chips, sawdust, and other agricultural waste. Sewage may be directly mixed with organic matter and composted in open windrows or in a ventilated building. Such processes require a great deal of biomass, but the biomass may be dried in the sun with mechanical turning and then reused to soak up more sewage. The systems may be used only if flows are small. Composting has most successfully been used on sludges from any of the unit operations discussed. Composting techniques were developed in China and India in ancient times, rediscovered in Europe in the 1800s, and recently have been utilized in the United States. Sludges may be composted without addition of organic matter but are generally too moist. Some bulky organic matter, such as the organic portion of solid waste, should be used to blend with the sludge and chipped media to entrain air and soak up moisture. Moisture content should be kept at about 65 to 72%. The easiest and least expensive composting technique involves using partially dried recycled compost, some new bulking agent, and sludge mixed with a front-end loader or with mechanical mixers to the correct moisture content. The compost is then windrowed and turned inside out, outside in several times at about 1 month intervals. An even simpler technique involves collecting leaves or other biomass during the year, piling the bulking agent in windrows and pouring sludge into a depression shoveled along the length of the windrow. Such simple techniques and a 6-month curing period will assure sufficient pathogen kill to allow use of the compost on base shrubs, lawns, or parks. A more elaborate scheme has been developed by the USDA. In this system, blowers, aeration pipes, and usually a roofed building allow for more rapid curing and a more continuous sludge processing. By this system, about 2.5 dry tons of sludge may be composted per acre, including space for the building, office, runoff control, and adequate landscaping. Before any composting technique is used, a belt of trees should be established surrounding the work area for odor control, which is paramount in composting, dust, dampening, and seclusion. Partially finished compost combined with fresh sludge has been treated with earthworms, which stabilize compost even more rapidly. Earthworms may be removed from the compost by drum screening, but their main function would be to speed up sludge stabilization and produce an easily handled granular soil amendment from what had previously been a noxious slurry. Soil biota are capable of stabilizing most organic wastes, including oily sludges. Today, only about 25% of sludges are spread on land. Even less are composted. However, the organic materials in sludges are beneficial in restoring fertility to soils disturbed by mining, gravel operations, or poor agricultural practices. There are, however, some major limitations. Concentrated sludges, if not composted or otherwise stabilized, placed on land should be immediately covered to prevent odor production and insect breeding. Sludges can be sliced or injected into soil or into stubble using special equipment. Deep snow and deep frost will stop land spreading operations. Although heavy metals concentrations in some city or industrial sludges have prevented their agricultural use, this limitation should not apply to waste sludges. The next advanced wastewater treatment process that we will look at is for nitrification. Nitrification occurs in 2 steps. First, ammonium is converted to NO2. Then the NO2 is converted to NO3. Both of these are bacterial processes. This process is limited by the relatively slow growth rate of Nitrosomonas. The following discussion is mainly applicable to activated sludge processes and nitrification. Additional information may be found in EPA Process Design Manual for Nitrification for Nitrogen Control. First, single-stage nitrification. When nitrification utilizing the activated sludge process is designed as a single stage, a longer detention time, 12 to 24 hours as compared with the usual 2 to 8 hours, is necessary in the aeration basin in order to provide an effective microbial population. This is interpreted in terms of mean solids residual time, abbreviated SRT, which is defined as the amount of mixed liquor, volatile suspended solids under aeration in pounds divided by the sum of suspended solids wasted and suspended solids lost in the effluent in pounds per day. The mean solids residence time will be maintained at 10 to 20 days or longer, depending on the temperature. In terms of hydraulic detention time, 12 to 24 hours is typical. Temperature has a significant effect on the nitrification reaction rate, which approximately doubles for every 10 degrees centigrade rise in temperature between 6 degrees centigrade and 25 degrees centigrade. A minimum dissolved oxygen level of 1.0 milligrams per liter is sufficient for nitrification. However, since dissolved oxygen concentration is a critical parameter, the aeration system will be designed to provide residual dissolved oxygen of 2.0 milligrams per liter and pH 8.5 using lime addition if necessary. The optimum pH has been reported to be 8.4. Lime requirements will vary with the temperature and must be determined for each case. Nitrification consumes approximately 7.5 milligrams per liter of alkalinity per milligram per liter ammonium nitrogen oxidized. Nitrification can be inhibited by certain toxic substances such as halogen substituted phenolic compounds, thiourea and its derivatives, halogenated solvents, heavy metals, cyanides, phenols, and cresol. These, however, are usually associated with industrial wastes. The design criteria for single-stage nitrification in activated sludge extended aeration processes will provide for the following. Increased aeration tank capacity and additional aeration to maintain dissolved oxygen level at 2.0 milligrams per liter. A hydraulic detention time of 12 to 24 hours. Sludge handling equipment suited to light, poorly compacted sludge with recycle capacity of 100% of average flow. Food to microorganism ratio of less than 0.25 pounds biochemical oxygen demand per pound mixed liquor, volatile suspended solids. Sludge retention time during winter conditions in excess of 20 days, and lime feeding equipment to provide alkalinity at a rate of 7.5 milligrams per liter per milligram per liter of ammonia oxidized, and a pH between 8.0 and 8.5. Separate stage nitrification simply separates the nitrification process from the activated sludge process. A typical system is illustrated in Figure 3, which you will see shortly. The main advantage to this system is that it allows individual optimization of the activated sludge and nitrification processes in terms of hydraulic and organic loadings. The relationship between ammonia removal rate and mixed liquor volatile suspended solids concentration is shown in Figure 4. There is little sludge waste in the separate nitrification system, and total sludge recycle is to be used. Detention time will be from 3 to 5 hours based on influent flow with clarifier outflow rates between 500 and 800 gallons per day per square foot. Diffused air will be supplied at approximately 1 standard cubic foot per minute per gallon of wastewater treated. With regard to nitrification in trickling filter plants, low biochemical oxygen demand loadings, less than 5 pounds per day per 1,000 cubic feet, and high wastewater temperature, 20 degrees centigrade or higher, are necessary for good nitrification in the 80 to 90% range in trickling filters, although they are often run at 12 degrees centigrade with some loss of overall efficiency. A trickling filter filled with plastic packing can obtain 90% nitrification of secondary effluent at a loading rate of 0.05 gallons per minute per cubic foot. Year-round nitrification facilities must be designed for the lowest wastewater temperatures experienced in the winter months. In this instance, the required filter volume will be much greater than that required for seasonal nitrification and will require at least two-stage treatment. With regard to rotating biological contactors as nitrification units, 90% nitrification can be accomplished using rotating biological contactors if the influent biochemical oxygen demand is less than 150 milligrams per liter and the hydraulic application rate is 2 gallons per day per square foot or less. For further information, refer to the EPA Process Design Manual for Nitrogen Control. Figure 3 is an illustration of the separate stage nitrification process. Figure 4 is a representation of the relationships in the nitrification tank loadings. Ammonia in the molecular form is a gas which dissolves in water to an extent controlled by the partial pressure of the ammonia in the air adjacent to the water. Therefore, ammonia removal from wastewater can be accomplished by contacting water droplets with large amounts of ammonia-free air. This process is desorption, but is commonly referred to as ammonia stripping. For additional information, refer to the EPA Process Design Manual for Nitrogen Control. Now we will look at denitrification, the suspended growth denitrification. Denitrification is performed by heterotrophic anaerobic organisms and therefore requires an organic carbon source and anaerobic conditions. Suspended growth denitrification will provide gentle mixing, no aeration, with the mixed liquor being clarified. The effluent is aerated to provide dissolved oxygen and to drive off entrained nitrogen, and the sludge is recycled to the contact tank. Methanol is the most common organic carbon source used and is usually applied at a dosage of 2 to 4 pounds methanol per pound of nitrate nitrogen removed. This dosage will be carefully adjusted according to nitrate concentration and temperature in order to avoid the effects of underdosage and overdosage. Raw or partially treated sewage and sludge can be used as a carbon source but yield lower denitrification efficiencies. Typical design factors for this system include mixed liquor, volatile suspended solids, concentrations of 1,500 to 2,500 milligrams per liter, detention time of 4 hours, clarifier overflow rates not more than 600 gallons per square foot, dissolved oxygen levels of up to 0.5 milligrams per liter, pH 7.0, optimum pH from 6.5 to 7.5, 5 minutes of effluent aeration, Sludge recycle from 50 to 100% of average flow. Temperature effects are very significant and should be kept in mind when designing contact tanks, since a 10-degree centigrade decrease would require twice the tank capacity. Fixed denitrification utilizes a flooded packed column with denitrifying microbial populations attached on the media surface. Sand, activated carbon, gravel, coal, and plastic packing can be used, with the finer media having shorter contact times. Columns can be either downflow or upflow configuration. Upflow columns have much longer contact times and operate at lower hydraulic loadings, but they are more efficient at lower temperatures than downflow columns. Temperature, again, is a very significant factor affecting denitrification efficiency. Typical design factors for both downflow and upflow denitrification are given in Table 6, which you will see. Fixed denitrification is capable of nitrate removal efficiencies of over 90%. However, the efficiency of the overall nitrification denitrification process is limited by the performance of the nitrification system, that is, around 90% nitrogen removal. Table 6 provides typical performance parameters for fixed growth denitrification, including, as you can see, contact times, hydraulic loading, media size, methanol dose ratio, moles of methanol to moles of nitrogen, dissolved oxygen level, and column depth. In three-stage biological systems, they are essentially a combination of separate stage nitrification and denitrification. The advantage of this system is the flexibility of operation, and the main disadvantage is the capital cost involved. This configuration also works to prevent short-circuiting, which can be a problem in nitrification denitrification when plug flow is not achieved. The specific design factors are the same as for the individual processes involved. Three-stage biological treatment can achieve nitrogen removals of over 95%. Figure 5 is a representation of the three-stage denitrification process. The anaerobic contact process, a further development of the high-rate digestion process, allows separation and recycling of digested sludge solids. Like the activated sludge process, detention and mean cell residence times are controlled. Denitrification within these contact vessels approaches 95%. The remainder of the presentation consists of a glossary which may be helpful to you in the future. This brings us to the conclusion of this discussion. I hope it has been helpful to you and will allow you to move forward and address advanced wastewater treatment projects as they come across your desk in the future. So have a nice day. Thanks a lot. Bye.